Good morning. We are almost at 10% mark. Okay, the next one is actually a hard level. I'm usually not able to solve hard levels problems at all. Let's just have a look. We will try our best. Let's just try for 40 minutes. If it's not going anywhere, then we will just give up and learn instead. Okay, entry studying in the line. Rating value. Higher rating get more candies. I mean, the construction of this question is okay, so each child must have at least one candy, and for all of them, the one that has higher rating has to have more candies than their neighbors. I see. So this child has to be given more candies than this, and this child has to be given more candies than this. And since these two are not neighbors, it doesn't matter. But this child has to at least have one candy, so that means these two must have two. Okay, so I guess it's a good idea to start with the children with lower ratings, which sounds so awful. I mean, come on, don't say stuff like each child is assigned a rating. Okay, example 2. So first child gets one candy, second child gets 2 candies. So they have the same rating, which means that they don't need to, which means they could I mean this expression is not stringent, because if you think, okay, this child has a higher rating than this. Okay, I guess what it means is if this child has higher rating than that, then this child gets more candies than that. But if this child has same rating as the neighbor, then they don't have to have the same amount of candies, or then it doesn't matter. Apparently this child could have 1 candy and this child has 2 candies. Okay. Let's start with constructing a bigger example. Let's try that. So how do we approach this problem? What if we start from the ones that have the lowest rating, so the zeros? they will get 1 candy. So they will get 1 candy, and first one gets 2 candies. And this one gets 2 candies. This one gets 2 candies. This one just needs 1. This one needs 2. So this one needs 3 candies. What about this? 2 candies. 3 candies. 1 candy. Okay. So how did we approach this? First, we found the lowest ratings. We assigned 1 candy to them. Then we go from the neighbors of these lowest rating ones, and we increment 1 candy. And then so that seems to be intuitive. Let's see. So we have those and those. And now what do we do? So we know if we are looking at this, we know that. Okay, so now we look at the neighbors of all the ones we already have. Okay, we look at this. Neighbor 3 is higher, so it has to be more candies. What about this? Neighbor is higher, more candies. What do we do when the neighbor is lower? We can assign 1. So even if this was 4 or 5 or anything, we could still assign 1. And then this is higher, so we assign an increment. And this is lower, so we assign 1. So this approach should work. How would we be able to translate this to an algorithm? So first we find out the lowest ratings, we assign 1 candy, then we go look at their neighbors. If we increment 1 candy for all their neighbors. So that's step 1, step 2. And then we look at the neighbors again. If neighbor is higher, we assign 1 more. If neighbor is lower, we assign 1. Would that contradict some cases though? Like if neighbor is higher, we definitely need to assign 1 more. What if the neighbor is lower? Okay. Like in this case, if we had 2 here, so we see 2 is lower, we cannot assign it to 1 because we might have even lower neighbors, then that has to be higher than its neighbor. So this would have been 2, but we cannot know just by knowing that it's lower. Okay, so higher increment, lower we will have to see. So what about we always find the lowest rating elements, assign them to the first round of lowest rating elements, we send them 1, and then their neighbors all get 2, and then we look for lowest elements again. Okay, so it's not correct to assign 1 extra just because it's a higher rating neighbor either, because that might have another neighbor. Okay, so for instance, if it was like this is assigned 1, and first I thought, okay, it's higher, we can assign it 2, but that does not work because this will be assigned 2, and this is higher, so that will be assigned 3. So should we always go find the lowest elements again and try to assign those first? Let's see if that works. Yeah, so this is the case. So we assign 2 here, but that does not mean we can assign this 3 because we might have the other side that needs it to be even higher. Okay, so let's see. We first assign all the lowest ratings. Okay, then we go through its neighbors. So let's say if this was 5, then actually this will be 5 as well. So it does not work if we just go to all these lowest rating neighbors and assign them 2. That does not work. so what if we do something like now let's find all the lowest ratings again. We have 1, 1, 1. What does that mean? Okay, what about we check? Okay, we found the lowest elements again. What are their neighbors? Okay, neighbors lower, so this will be 2. Both neighbors are higher, so that'll be 1. This is 1, so this has to be 2. Let's see if this works. Okay, next round we will find out the 2's. Here we have a 2. Okay, that'll be 2. Here we have 1 and 2, so that'll be 3. Here 1. Okay, this seems to be working. Alright, 3, 3, 2, 2. Now the 4's and 5. Okay, I think that works. So the algorithm I have right now is, first I find all the lowest rating elements, we assign them 1, then we find the next round of lowest rating elements, and we look at, for each of them we look at their left and right neighbor to assign their correct value. Then we repeat that until we are done with all the elements. So this is definitely brute force. I mean, it might work, but it might be time limit exceeded. Let's see. So there might be way better ways to do this, but this is what I have so far. So let's try that. It's definitely not efficient because for each round we are trying to get the lowest rating elements again. If we traverse every time to find the lowest element, that will be linear for each time, and we will be doing it corresponding to how many elements there are, so that will be quadratic. Is there any way we could be more efficient there? What if we set up a dictionary and store the indices of each element? So for instance, we have 0, and then we store, okay, the 0 elements are at index 1 and index that. Then for 1, they're at those index. So at least we don't have to traverse it every time to find the next round of lowest elements. We can just pick up directly from the dictionary. Okay, I think that might work. Let's try that. So we want to save their indices, and we also want to be able to get the next round right away. So dictionaries, the keys are not ordered. Could we do this in a list instead? mean, we could do a list of lists, and then in each list it is each list is the corresponding indices, but then we don't really have that key value. I guess we could use tuple to store the key values in the first place, and then the list of indices in the second place, and then we can try to order these tuples by the first element. Okay, I'm still new to Python, so I will have to figure out the syntax to do that. And if I do use a dictionary, then I have all these keys, which keys are the value of the elements. And then we need a way to order these keys so we are able to get to the next round efficiently. Let me search Python dictionary order by key. Is that possible? I think that might work. Let's try that. So that's a dictionary we have. Okay, we are putting the keys in a list. We sort that. Then the sorted dictionary would be, okay, key and value. I guess I could use this. Yeah, okay. We will try that. So, oh my god, it's already been 23 minutes and I haven't even written anything. So, this is a dictionary of the indices for each element. Let's call it indices. Do I need to initialize a list? Maybe. Not quite familiar with Python. Let's just try it. If reading not in indices, and then no, this is a list. Okay. Otherwise, we just append we actually need the indices here. Yeah, okay. So now we have this dictionary. And what do we do here? For the values for the keys in sorted dictionary keys. So now we should have the lowest key value. I should also look up how to initialize Python initialize array with size none times. Okay, if that's the way, because that's not how you do it in other languages. Okay, so for that, for the lowest key, zeros. So the dictionary 0, we need to get the indices for those. For each index in that list of indices. If ratings index is 0, then we set this to 1. Otherwise, it's not 0. What if we skip? We could Right, yeah. Okay, we're not doing anything, we're not putting this to 2 and 2. You just need to go to the next round and check. Okay, if it's 0, then it's 1. Otherwise, let's say it's 1. Okay, otherwise we need to check if index -1 or index +1 equals to length of radius. Then we know it's on the edge and we can just skip these. We'll just continue to next round. So that index doesn't need to be checked. So here, -1 is not within the array. We just continue. Otherwise, we want to check both left and right and then decide what it's gonna be. Otherwise, we might need to initialize this as 0. Let's see if we let me just put a note here if we might need this to be 0. Okay, otherwise Candy's index should be the maximum of Candy's the left one and the right one +1. So that's what I'm thinking for all the, we do this for all the indices, for all keys. Okay. Let's see if this is close to correct. Wrong answer. Okay. Let's see what happened. 0. here only slept 4 hours. Key is 0, 1, 2. That is correct, at least 1 and 2. Okay. For each index, okay, so we are here. If ratings is equal to 0, then we get Candy's index is equal to 1. Let's have a look. Okay, so first round worked. Now, next round, K is 1. K is 1. Oh, I see. Okay, if the left one is, so if this is the left edge, then else if it's the right one, then we do left one minus 1. Otherwise, it goes to both sides. Okay, so that is fixed. What about case 2? Okay, let's look. K is 1. Okay, 1 index is 1. I'll go there. Now next round, K is 2. Index is 1, which means this Candy's 1 will be assigned to so it will only be assigning higher when it's higher than its neighbors. Okay, so this case that's higher than both neighbors. So this case, that's what's wrong here. If okay, so the right side is the end, so we don't need to look at that. If it's higher than the left side, that's when we assign it to 1 plus. Otherwise, we assign it to 1. But this feels like a lot of redundant. Okay, let's just fix that first. See if we can refactor later. Okay. Oh, right. Oh, God, I'm not thinking well right now. Really need to rest. Well, you passed some test cases in it, but not all. Let's see what the problem is. I see. Okay, so we are here. We're standing here. We're looking at this index 1, which is just 2. That's why it's assigned 3. So this should be 3, 3, 1. that's 3. If okay, so it's only when it's bigger. One is bigger than the right one, then we increment. One that's bigger than the left one, we increment. This is only when it's bigger than. If it's bigger than the, but that seems to be. Okay, definitely we'll be able to refactor after this. Let's see. So we have 1, 2. This should be 3. And right now this is 0. So we have 2 and 0. This should be 3. So if it's bigger than. If it's bigger than both of them, then it takes the maximum. So that gives a 3 here. So we have 3. And the next one we have here is actually 3 and 0. Well, actually, if it's bigger than the left one, then I should increment 1 from the left one. And if it's bigger than the right one, then I should increment 1 from the right side. What if we just do that? So that gives us 3. So we 3, 0. Nothing happens. There will be assigned 1. We have 1 and 2. That will give us 3. So 3, 1, 3. Okay, that should work. So if it's if it's bigger than the left one, then this order is not okay because it needs to take the maximum of them. Okay, this is looking really bad. We'll definitely need to refactor, but let's just make sure this logic is working. Okay, let's just see if this logic is working first. but also if it's not, then it should be assigned 1. Okay, alright, I'm glad that the logic works. It's obviously not efficient. Mm-hmm. Okay, so it works, but it's not efficient, so there are better solutions. It's almost an hour now, so let's do the time and space analysis for this first, then I will give it another few minutes and see if I can come up with anything. So let's see, what are we doing here? So this for loop, we are, for each element we will put their value and their indices in this dictionary. So that is linear. Now we wanna sort the dictionary by keys. So then we start from the lowest value keys, which mean the lowest rating elements. So we are doing that in this bigger for loop. You no longer need to print these. That did save us some time without the printing. Okay. Then for each lowest value rating for this round of same rating, we are gonna check each element, and this is for the case if it's the leftmost one, this is the rightmost one, and otherwise we need to check both left and right and increment. If it's smaller, then we just take 1. If it's bigger, then it needs to be bigger than the left or the right one, and we take the maximum of it. So what is the time complexity for this bigger loop? I mean, I know it is 2 for loops, but we first have categorized these. So the entire input is linear, but we categorize them. We have already categorized by keys, by different categories of values, the ratings. And then for each category, each group, we will go through all the elements once. So essentially, I would say that this is linear because these two combined will be checking every element. We are just checking each element in the input once because we already stored all the information we need in the dictionary, so we know where they are. We just go there and we do some comparison. So I do think that this is a linear time solution. Space would also be linear. We're using a list to store the results and a dictionary. So linear time and space. It doesn't look very efficient, but I'm not sure how I would be able to improve from linear time. I guess there must be a better way for all of this because this looks redundant. Okay, 2 more minutes, then I'll give up. I'll finish my breakfast. So if the left one is not out of the array, and the left one is bigger, then we increment. Otherwise, A is just 1. And if the right one is not out of it, and so I think that might be the right way. Zero. If it is 0, we might not need that either. Let's just check this first. Okay, that works. It's a little better, I'll say. Okay, yeah, 40%, that's a little better. So we might not need that either. Wow, apparently that made all the difference. Huh, I'm kind of surprised that made so much difference. Okay, I guess this solution is good after all. Alright, the time difference not that much. Interestingly, the print took so much that I thought this was not the right algorithm. Okay, so now we have this linear time and space solution, which is good. And we have refactored this part. All right, I think now I'm happy with this. Okay, it's already been 1 whole hour, but let's just take a few minutes to look at other people's solutions anyway, just quickly. Oh, this seems like a completely new way to do it. Okay, I will need more time to think about that. So I will conclude my video here. I am pretty happy that I actually managed to solve this hard problem. Usually I don't even attempt to solve hard problems at all. Maybe this is actually easier than hard, I guess. But happy for this one. I will look at all the other solutions, and that's it for today. See you next time.